do charges interact? So the interaction between charges is very similar to that in gravity. So with gravity, what we want to recall is that when we have two masses, okay, so you could have the Earth as one mass, and you could have another object near Earth as another mass like this, and you would have these two masses feeling a force of attraction between the two. So what we would do is we would say, okay, so along this line that connects their centers, their center of masses, like this, there would be a force on the Earth pulling it towards the direction of the other mass, like that. Some force, F, subscript G for gravity. And on this other mass, there would be another force pulling it with the same amount, just in the opposite direction. So along the same line, noticing that the forces are towards each other, like this. So, and the masses were always positive, so the forces were always attractive towards each other. So, now in electricity, so versus electricity, okay. In electricity, we have that there are two kinds of charges, positive and negative. So it's associated with their positive and negative charge values. So let's say if we have a proton or some positive charge, and we have an electron or some negative charge. We draw that line that connects the two together, let's say like this. It's almost like a shish kebab. Delicious particles. So we have some positive and negative charge. So we'll find that this picture behaves a lot like this picture, where two different kinds of charges or opposite kinds of charges will attract each other. So the positive charge is pulled towards the negative charge with some force, call it F subscript E for electric force. And the negative charge will feel the exact same force in the opposite direction, so along the same line, just towards the positive charge. So it attracts towards the other charge. Okay, so we find that this picture is a lot like this picture over here for gravity. So then if we have the other case, though, where we have like charges, so this one was unlike charges, and they attract. For our like charges, or the same kind of charge, so for the same kind of charge, whether if it's a positive and a positive or a negative and a negative, regardless. Let's say I draw it with two negatives. Okay. Regardless if they are the same kind of charge, and we draw the line that connects the two like this to draw our forces along, the forces will still point along this line, but just in the opposite direction of each other. So the force on this one will be away from this one along this line. So along this line down to the left in this picture, there's our electric force. And this one, the same, away from the other charge. Same magnitude or same size, opposite direction. Okay. So we find that two like charges will repel each other. So the forces are repulsive. We use the terms attract and repel when we want to talk about forces that will either pull something towards or away from something else. Okay. So this is the nature of the direction of the forces, and because of the two kinds of charges, we get two different behaviors as opposed to gravity, where it's only attractive. Now, how do we calculate or quantify this amount of force? So we have Coulomb's law. Okay. So Coulomb's law, if I can spell it right, will give us the magnitude or the size of electric force between two point charges. So basically point charges being little points of charge or things that resemble points, so like little tiny spheres. They have to be able to resemble point charges. So given that we have, let's draw another diagram for this. So we have our two charges along the line. Say we use positive and negative as our example. So we know that there's a force of attraction between them, or repulsion if it's the same kind of charge. Now, if we were to label some things in here, let's say there's some distance between the two. Let's define that distance from the center of this charge to the center of that charge. And ideally, if they're points, then the center is the point. This distance we're going to call r. Okay? That's the distance between the two charges. So the equation that describes the force between these is the following. The electric force, F subscript E for electric force, equals, I'm going to use absolute value bars to indicate that all of the numbers that we put into this equation does not matter in terms of its sign, so positive or negative we're going to neglect. We will plug it all in positive, simply because we're only going to get the magnitude. The direction is taken care of by our conceptual knowledge of knowing what happens to unlike and like charges. So we have that the magnitude is equal to K, let's call it capital Q, lowercase q, divided by r squared. And you can also put K in the numerator. Now, each of these, so we have, if we define these, K is equal to 8.99 times 10 to the 9th. The units of this are determined by the units of everything else. So the units of K are actually just the flipped units of all of the rest of the things. So in other words, we have, it's going to be Newton meters squared over Coulomb squared. If you ever forget the units of K, you can just solve this equation for K and look at the units of everything else, and that's what it's going to be in. This is called Coulomb's constant. Okay, so this guy gets everything named after him. So he has his own equation, he has his own constant. So that's just a given constant. These Q's, sometimes it's called Q1 and Q2. I'm going to more generally call them capital Q and lowercase q. So these, capital Q and lowercase q, are both defined to be the charges. Okay, and everything is implied to be in standard units, so that means that the standard unit of charge is going to be in coulombs, and that's what we need to plug it into the equation as. So those will be our charges. So in this case, in this picture, we might call this one capital Q, and we might call this one lowercase q, which we could later rename to Q1 and Q2, or if we have more charges, they could be Q2 and Q3, and etc. And then finally, R is defined to be the distance between the charges. Okay, so it's that direct distance that directly connects the two charges. Now, one last little piece that we'll put into this, because we are talking about forces. Forces are actions, and it's going to cause these to do something. So if we do want to talk about what these charges will do, we'll also recall Newton's law, Newton's second law specifically. Okay. And it states that the sum of all forces acting on some mass or system equals mass times acceleration. Okay. So this describes the force on some mass, which we would plug the mass of that particular object of interest into this equation. So let's say in this picture here, if I wanted to find, if I wanted to talk about the acceleration of one of these two, I would plug in the mass of whichever one I'm trying to find the acceleration on. So we can use Newton's law to further talk about what could happen as a result of the forces or multiple forces acting on these objects.